signal x of n to the FIR or AIR filter, that is finite impulse response or infinite impulse response filter, which has a transfer function W, and we get an output signal y of n, which is then compared with the desired signal d of n to find out the error signal e of n. Basing on the error signal e of n, we use an adaptive algorithm to find out the correction that has to be given to the filter, and that is delta Wn, which is then passed to the filter, and the output signal thus converges to the desired signal. There are two main different types of adaptive filter correction algorithms: the least mean square algorithm and the recursive least squares algorithm. These two are the widely used and the two basic types of adaptive filter correction algorithms. Let's go in detail about them. The least mean square adaptive filters. The LMS algorithm consists of two basic processes: filtering process and adaptation process. So in the filtering process, the output of a linear filter in response to an input signal is computed, and then the error is estimated by calculating by comparing the output and the desired signals. And in an adaptation process, we adjust the tap weights based on the estimated error. So, to determine the optimum setting of weights so as to minimize the difference between the system output and some desired response D in the mean square sense, the input-output relation of the filter is given by y equal to sum of wk and xk. If we denote D as the desired response or the target output for the filter, we get the error signal as the difference between the desired signal and the output of the filter. So, as a performance measure or a cost function, the mean squared error is defined, which is half of expectation of e square. That's the error signal square. So, now we have to determine the optimum set of weights for which the mean squared error j is minimum. So, we carry forward by substituting what e is here, and by proper calculation and simplifying the terms, we arrive at the result. So finally, j equals to half rd minus, where rd is equal to expectation of t square, minus sum of wk rdx of k plus half of sum of wj wk rx of jk. Finally, we arrive at the adaptation rule. W of k plus 1 equal to W of k plus mu into E of k into x of k. So, as a summary, we have here the LMS algorithm is written in the form of three basic relations as follows. Filter output, y of n equal to W power h of n into x of n. Estimation error or error signal is given by the difference between the desired signal and the output signal. And we have tap weight adaptation, that is the adaptation rule, as W of n plus 1 equal to W of n plus mu into x of n into e power n. The scaling factor used in the computation is denoted by a positive quantity mu called the step size parameter, which is taken as 0.6 in my project. So the final adaptation rule again, as a reminder, is update value of tap weight vector equal to old value of tap weight vector plus learning rate parameter into tap input vector into error signal. And now let's move forward to the recursive least squares adaptive filters. The use of method of least squares is extended to develop a recursive algorithm for the design of adaptive filters such that given the least squares estimate of the tap weight vector at iteration n-1, the updated estimate of the vector at iteration n is computed upon the arrival of new data. The resulting algorithm is referred to as the recursive least squares algorithm or filter or just RLS algorithm. Again, we have a couple of equations here. The cost function to be minimized is given by epsilon of n equal to sum of beta of n comma I into absolute value of e of I square, where e of I is the difference between the desired response d of I and the output. That is error signal equal to d of I minus y of I, which is again equal to d of I minus w power h of n into u of I, where u of I is the tap input vector at time, defined by u of I equal to u of I minus 1, and so on till u of I minus m plus 1 whole power t. And finally, w of n as a tap weight vector at time, defined by w of n equal to set of w0 of n, w1 of n, and so on till wm minus 1 of n power t. So basically, on recursively squares, our aim is to be able to recursively update our linear least squares estimate x bar as we add more observations. At time or an iteration k, we want to find a least square estimate xk equal to ak into bk, where for each new k another measurement is taken so that ak equal to ak minus 1 and ak in a matrix with column 1 and 2 rows, and bk equal to a column matrix of bk minus 1 and beta k. And this way, as we progressively obtain more and more measurements, we should also be able to refine our estimate. We could recompute equation 1 from scratch at each k for the matrices are growing in size, so computations will take longer and longer. However, if we write xk bar equal to ak bar t into ak whole inverse into ak bar t into bk, which is again simplifies to ak bar t bk, then we get phi of k equal to, like suppose phi of k equal to ak bar t into ak and ck equal to ak bar t bk have sizes independent of k. Observe that there are recursive update formulas for phi k and ck. So we have phi k equal to a row matrix of ak minus 1 bar t, ak bar t into a column matrix of ak minus 1 and ak, which gives you ak minus 1 bar t, ak minus 1 plus ak bar t ak equal to phi of k minus 1 plus ak bar t into ak. We have ck equal to ak bar minus 1 t into ak bar t into column matrix of bk minus 1 into beta k, that equal to ak minus 1 bar t into bk minus 1 plus ak bar t into beta k, that equal to ck minus 1 plus ak bar t into beta k, where we initialize with phi naught equal to c naught equal to 0. Since the sizes of the matrices are fixed, so is the amount of computation required at each iteration. Using block matrix inversion, we can obtain an arguably more elegant recursion, avoiding the need to calculate matrix inverses. Using the Sherman-Morrison-Woodbury-Schur, that is SMWS formula, it turns out that phi k bar minus 1, the inverse of phi k equals to phi k minus 1 plus ak bar t into ak whole inverse, that is equal to phi k minus 1 inverse minus phi k minus 1 inverse into ak bar t into 1 minus ak phi k inverse into ak bar t whole inverse ak bar ak into phi bar 5 inverse phi k minus 1 inverse. Writing pk equal to phi k inverse, we have a new recursion, the particular form of which involving a square of pk minus 1 is known as Riccati equation. That is pk equal to pk minus 1 minus of pk minus 1 ak bar t ak pk minus 1 whole divided by 1 minus ak pk minus 1 into ak bar t. Now, to learn more about the gain vector and the production error, xk bar equal to pk into ck, and if you substitute the value of ck here and go on simplifying it, you arrive at the formula xk bar equal to xk minus 1 bar plus kk into epsilon k, where we have above defined